in order to cultivate the skill of drawing stereoisomers, prediction of the number of stereoisomers, and also drawing them, let's now take another example. And of course, we will also use Fischer projections, okay, just like or in addition to the method that we learned before, which is the tetrahedral drawing. This time we use Fischer projections. Let's take 2,3 dibromo, 2,3 dibromo butane. And if you look at this molecule, you will see that this molecule has two chiral centers, two stereo centers. This is one of them, and that's the other. So there are two stereo centers or two chiral centers, and therefore, initially at least now, just following the 2 to n formula, if you like, you would be able to predict 4 stereo isomers accordingly. So 2 to 2, therefore, this leads us to 2 to 2. So 4 stereoisomers. In 2,3-dichloro, 2-bromo-3-chlorobutane, the stereoisomers, there were 4 stereoisomers, of course, 2 pairs were enantiomers, and any relationship between any other 2 was diastereomers. Let's draw the possible stereo isomers in this case and see how we can analyze them further. But before that, it's very important to note that the two chiral centers are actually identically substituted, which means this carbon has this bromo group, the two bromoethyl or bromoethyl and methyl and hydrogen, of course, each of these, and the other one has the same group, so each of them has Br, hydrogen, bromo ethyl, and of course methyl. Each of these stereo centers, again, if you look at stereo center number 2, for example, it has Br, hydrogen, methyl, and this group. If you look at this stereo center, you would see that it has a methyl group, a bromo group, a hydrogen, and the bromo ethyl group. So these two stereo centers are identically substituted. This is very, very important to note. So the chiral centers here are identically substituted. Now this will lead us to an important point which we will discuss at the end of this lecture. So let's begin with drawing the first stereo isomer. So this is the first one. This is the first stereoisomer. We simply now draw the mirror image of it in order to get its enantiomer, or its mirror image if you like. So if we put a mirror plane, then we would be able to draw the mirror image of the first stereo isomer. So this is stereo isomer number 2, and this is number 1. So two possible two stereoisomers so far that we have drawn. In order to draw the third one, as we did before, you keep the absolute configuration, if you like, or stereochemistry at C2 or C3 fix, and then you reverse the other. So again, whichever you do it doesn't really matter, because in the end we will draw the mirror image of it in order to get the fourth stereo isomer. So this is the fourth one. The third one, this is the third one. We keep the top or the stereochemistry at C2 fixed, for example, at that chiral center, but then we reverse stereochemistry at the second. So we kept this stereochemistry exactly the same. So there you go. And the second one is actually a reverse. So basically you swap again the positions of this hydrogen and bromo group. Now, if we draw the mirror image of this, of this stereo isomer, then we would get a fourth one. So this is number 4. Number 4 is simply the mirror image of 3, and that's exactly following the practice that we did before, which is the correct one in order to draw all possible 4 stereo isomers. If you look at 1 and 2, you could tell clearly that 1 and 2 are actually enantiomers. So 1 and 2 are enantiomers. So these two are enantiomers. Now, if you look at 3 and 4, okay, they are, you might say they are enantiomers, but if you look at 3 or 4, it would be possible actually to draw a plane of symmetry. To draw a plane of symmetry. So if you draw a plane of symmetry here, okay, then this cuts the molecule into 2 halves, which are mirror images of each other. So number 3, therefore, and so is number 4, because number 4 is a mirror image of it. These 2 stereoisomers have a plane of symmetry, therefore they are achiral. 3 and 4 are actually identical. They do not represent different molecules or different stereoisomers. 3 and 4 have a plane of symmetry, so this has a plane of symmetry, and so of course so is 3. 3 has also a plane of symmetry. Therefore 3 and 4 are not chiral, whereas of course 1 and 2 are chiral. Yes, it is true they have stereocenters, of course, and they don't have plane of symmetry. So each of these is actually chiral. So 1 is chiral, 2 is chiral, 1 is chiral, 2 is chiral, but 3 and 4 are achiral. None of these is actually chiral, despite the fact that they have stereo centers. That's because they have a plane of symmetry. Now 3 and 4 are actually the same compound. They're identical. 3 and 4, since they are identical, of course, they represent the same stereoisomer, and 3 and 4 are called actually meso. So this is an example of a meso compound, basically a meso compound or a mesostereo isomer, if you like, is a stereoisomer that has chiral centers, of course, but it has a plane of symmetry. Of course, it is achiral. If you check alpha D or the specific rotation in the polarimeter, you will find out it's actually 0. So alpha D of any meso stereoisomer is actually 0. It's achiral, of course. This is very important again. So meso is achiral. That's because it has a plane of symmetry. It will not rotate a plane polarized light. Its alpha D is actually 0. Now, so are they actually 4? The answer is actually no, they are not actually 4. That's because there is a meso compound and a pair of enantiomers. So 1 and 2 are actually a pair of enantiomers, whereas 3 and 4, of course, there is no 3 and 4. It's only 3, because the 3 and 4 actually, as we learn now, they represent the same stereo isomer. Therefore, they are a meso compound, if you like, or a mesostereo isomer. So if this should be corrected, therefore, and we correct it to 3. So there are not 4 stereoisomers. There are actually 3 now. That's because of the same observation that we came up with, which is that the two stereocenters are actually identically substituted. So if the 2 stereocenters are identically substituted, it's not 4 stereoisomers that are possible. It's actually 3, because 2 of them would be enantiomers, and the third one would be a meso compound, basically the stereoisomer that has a plane of symmetry. So 1 and 2 are enantiomers. 3 and 4 represent identical stereoisomers. So 3 and 4 are exactly the same. They do have a plane of symmetry. They represent a meso compound or a mesostereo center whose alpha D again is 0. It's achiral. Okay, one is chiral, 2 is chiral, 3 is achiral. It will not rotate the plane polarized light again. So 1 and 2 are actually enantiomers. Three is a mesocompound. And the stereochemical relationship between 1 and 3, and of course 2 and 3, as you might predict, well, diastereomers, because 1 and 3 and 2 and 3 are not mirror images, so they must be therefore diastereomers. So 1 and 3 2 and 3, these are diastereomers. So therefore, 2,3-dibromobutane represents an example of a compound which has 2 chiral centers, but in fact it has 3 stereoisomers, not 4 as somebody might predict at the first glance. That's because the 2 chiral centers, or the 2 stereo centers, are actually identically substituted. 2 stereoisomers would be non-superimposable mirror images with each other, therefore enantiomers, and the third one would represent or would be described as a mesocompound, which it is the stereoisomer that has a plane of symmetry. Remember, mesocompounds are achiral. They have an alpha D of 0. Specific rotation of mesocompounds are actually 0. That's because they are achiral, and of course it is 0. That's because they don't rotate a plane polarized light.